I'm Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering College. Today we are going to look at applications of single linked list. In the previous session we have seen what a single linked list is, how insertion, deletion, traversals operations are performed on a single linked list. In this session we are going to look at two basic applications of a single linked list, right? The major one is polynomials, representation of polynomials. Have a look at what a polynomial is. It is composed of coefficients and exponents. I hope guys you remember your basic maths where you write a polynomial in terms of p of x, where x is a variable. So it can be written in the form of ax per n plus bx per n minus 1 plus so on, so forth to a constant k, where a, b, c and c, d so on will be known as the coefficients of the polynomials, right? So how to represent a polynomial in a computer? So using single linked list, we can easily do that. So have a look at the structure of the single linked list, which can be used to store a term, a single term in a polynomial. It will have three parts: coefficient part, exponent part, and the third one, the address part. Then I hope you know what coefficient is and exponent is. Then what about this address part? Address part is having its significance. What address tells is the address of the next node. I hope you remember the structure of a single linked list, where the data elements are placed randomly in the memory, but they remember their next element with the help of its own part known as address part, right? So this will be the basic structure of a basic node when we implement a polynomial using single linked list. So what are the key points that we need to remember while working with polynomials, right? So the sign, the basic sign, positive sign or negative sign of a exponent or coefficient will be a part and parcel of the data, right? If, for example, have a look at the diagram which I have given you, 4x cubed plus 6x squared plus 10x plus 6. First term is 4x cubed. Here, the coefficient part is 4 and the exponent part is 3. So, while storing it using a single linked list, have a look at this picture. So, 4 will be placed in the first part of the node, 3 will be placed in the second part, whereas the address of the second term will be placed in the third part. What if it is not 4 but it is minus 4? Then even at the representation also you are going to place minus 4. Okay, so the symbol of coefficient or exponent becomes a part and parcel of the data, right? So that you have to keep in mind. Then additional terms having equal exponents is a possible one. For example, some novice has given that 4x cubed plus 2x squared plus 3x cubed. You can see that the first term as well as the third term are the same, right? Don't you find that? So they can be written as 7x cubed. Right? In linked list representation, we are going to place them in two different nodes. We are going to store them in two different nodes unless we perform an operation saying the nodes whose exponent part is the same, add the coefficients and convert it into a single node. That becomes a different story. That is totally a different operation in itself. Okay, but while storing, we may get additional terms. So storage allocation for each element will be done in ascending or descending order. Generally, we go in polynomials from higher part to a constant we travel, right? So in that manner, if you take, it will be easy for you to understand, right? So have a look at this picture keenly, how we have placed the coefficients and exponents of different terms. Look at the last node, 60 slash. So what do you mean by this? The simple meaning of this is, as 6 is a constant, 6 x per 0. Don't you feel that? So 6 will be placed in the first part, 0 in the second part. As 6 being a constant is the last part of our polynomial, and it is not going to further point to any other term, the address part will be having a null, right? So simply diagrammatically we have shown with a slash, but when we store, we are going to place null. Whenever in any node, if the address part holds value null or none, it means that it is the last. Simple. Whatever the concept you have learned in single linked list is being just extended. In single linked list, what we had, a node will have two parts. The first part will be the data part. Second part will be the address part. Address part holds the address of the next node. The only change, an extension, you can say that. Extension to that definition is, there the data was a single part, but here the data will have two parts, the coefficient part and the exponent part, right? So that will be a small extension. That's it. If you learn in this way, it will be quite easy for you to understand, right? So let's have a look at Python code to implement or to create a polynomial. So have a look at the class node. The constructor of the class node will have three parts, right? So the first part will hold the coefficient, second part will hold the exponent, and the third part will hold none, signifying that the node which you have created just now is not having any relation with anyone. You are the one who have to establish a relation, right? So the constructor will be passed or will be fed with the values of coefficient and exponent. So that is a basic class node to create a node in itself. Then comes the class polynomial. The constructor of it will have a start. That start is nothing but a pointer variable which holds none. At the initial state, it will be none, right? So then comes your create node. Have to create a node. Very simple. Read the values of coefficient and exponent. We have to place it, right? So integers I have considered int of input, the basic code in Python. So the fourth line goes with creating an object called as new node, right? So whenever an object is called, the constructor from its corresponding class will get invoked. And here I am passing whatever the coefficient and exponent, whichever I have read just now as the parameters. So now I can create a node, right? And I'm going to return the node. Whoever calls this function will get a new node with data in his hands, right? So now creating polynomial list. I have gone through how to create a node, how to place data in it, how to return it. But now the task is to make a chain of it, right? It's a chain of it. Let's see. So we never know how far I'm going to do this. That means the list can be, my polynomial can start with an exponent of 4, 5, 7, 10. It can be any value. So unless I give an exit condition, that means if I'm going to pose a question, do you want to still create a node? And if I say no, n, for which I'm going to use a character n. If I give n, it is going to break and come out of the loop. Unless I wish, I am going to continue creating the polynomial. That is the fun of this one. And this piece of code, have a look at this one. This is the one which is going to justify my words, right? So do you want to create a polynomial node and read a character? That will be stored in answer variable. If it is n, that means no, which signifies no. Break, which will come out of the while loop. And in the while, you can say it's true. That means what? It will come out. The while loop is going to break itself unless you press N. No, I don't want to further extend my polynomial, right? So everything is in our hands. So if I don't give N and any other character from the keyboard, it will take me to create a node, right? New node is equal to self create node. So create node is nothing but the function which we have seen just now. It will create, right? In creating, it will ask the values of coefficient, exponent. It will call the constructor of node and create. Now, as I said, the task of this function is to make a chain, to make a list. So now I have to think in that direction. So what if the start is none? Mane, it is not pointing to any node. Mane, no node is yet been created. It is a fresh one or an empty one. In that case, whatever the new node which you have created just now will be the first node. Start will be holding the address of the new node. What if? What if this condition in your if fails? That means start is no longer none. It is holding some address. Right? At least one node is already being created. Right? So now my task is to place the new node, whatever I have created just now, as the last element. Right? So let's do the same. Naming ceremony. Right? So whatever node which the start holds, the start pointer variable holds, will get a name temporary. So I'm going to take the hops. Unless that temporary next, that means the next part of temporary is none. That means, what did I tell you just now? Any node whose next part or address part is none tells that it is the last node. Once I reach the last node will hold the address of the new node. A chain, a new member in the chain gets linked to that, right? I hope you understood this piece of code, right? So now you can display the same, right? You can display the same temporary start from the starting one unless you reach the last node, you are going to print the value. So print coefficient and exponent. Remember, I'm talking about polynomials. There will be two pieces of data, not a single piece, right? And the DC, that's the driver code. Driver code, as you can see, I'm going to call it polynomial, then create polynomial list and a simple display function. This will give you the basic. Guys, try to implement this in your Python. Python is an open source, free source. Download it. Start typing on it. Be careful with the indentations. Okay. So be careful with that and do it. This simple program will help you to create a polynomial. When you display it, you will get a chain. A chain. You can see that chain. A chain which will, if I give that 4x exponent 3 plus 6x exponent 2 plus 5x exponent 1 plus 6 will be the answer, right? So this is how you are going to get, you will get to see how your polynomial looks like when you store it using single linked list in your memory, right? This is one of the applications of your single linked list. The second application goes with sparse matrix. Then, first of all, question yourself what a sparse matrix is. I hope everyone knows what a matrix is, right? Matrix is what? It is a combination of rows and columns, right? And how you going to get the size of a matrix? Number of rows by number of columns. Then when we call a matrix to be a sparse matrix, if the data in it, that is more than 50% of the data elements of that matrix are zeros. If more than that are zeros, then we call it as a sparse matrix. So why we use a sparse matrix instead of simple matrix? So to reduce the storage space, as I said, most of the values are zeros, and computing time will get reduced when we hold only non-zero elements, right? So using that, for that purpose we use sparse matrix. So sparse matrix, look at the example how it looks like when we use a two-dimensional array or a matrix to store the data. So have a look at that one, 00304, right? So in the first row itself, out of 5 locations, 3 locations are zeros. So have a look at the whole matrix, loads of values, more than 50% of its data is zero. So if we want to represent, if we want to convert this into a sparse matrix, we can convert using 4 different methods: array representation, linked list representation, list of lists, and dictionary. Let's have a look at all these 4 methods. Let's start with arrays. When we start with arrays, so we will have a fixed 3 dimensions. So 3 rows, row, column, and value. So have a look at the example which I have given over here, which we have seen earlier also. So 00304, right? So number of rows will be fixed, right? The first row talks about row value. The second row talks about column value. And the third row talks about the data value, the data part, right? So have a look at the combination of these values column by column. Okay, so let me explain you this. Consider this, right? So how you are going to name your matrix index values 0, 1, 2, and 3. Okay, go to the column 0, 1, 2, 3, 4. Am I right? So 0th row, he's talking about 0th row. Second column. What is the value? 3. To store that one. So let me pick randomly one and the value. Okay, let me take this one. 137 is talking about the row 1, this row. Third column, this column. And the intersecting point, you can see 7. 7 is the value. Okay, see how easily you can store data using a two-dimensional matrix, right? A two-dimensional matrix to store a sparse matrix. Look at the sizes. So have a look at your sparse matrix representation. You have that means the point of concentration will be your last row, the values. Do you see any zeros over there? Because I'm not interested in zeros. So all the combinations of rows and columns which are not mentioned over here are zeros, right? A simple representation. Then why we are going for linked list? Very simple example. Answer will be rows and columns, arrays, fixed size. You cannot extend it. If you want to extend it, dynamic methods, DMA, you have to use. Then it's better to, all the drawbacks of arrays are going to be placed over this phenomenon of storing or converting a matrix, a sparse matrix using arrays, right? So better go for linked list. Here I'm going to use a linked list with 4 fields, a small extension for the previous polynomial one. So here we have a row value, a column value, data value, and address value. That is the next one, right? So have a look at this diagram. Guys, it's very simple. Don't get panicked. Look at the diagrams. It's quite easy. So let's start with this one. For example, 0, that is a row. 2 is talking about column. 3 is talking about data. And this part is last part is talking about address. Okay, so this is how you can store, you can or represent a sparse matrix using a linked list. Obvious, you can extend it to any length. linked list is having that beauty. You can extend it dynamically if you want to insert in between or last, anywhere it is okay. But only drawback with your linked list is space, the extra space which it needs to store the address of the next node. That is the drawback, right? So even that can be overcome using list of lists, right? So it will have now what it is a representation, is a basic representation where rows and each row contains a list of triples, that is the column, value and address. Remember, I'm interested only in non-zero values, right? So have a look at this one. So the basic list of lists, that means a list is holding the addresses of the columns. Very simple, right? The structure of each node will be address of next node with a column index and value as it spans, right? So have a look at this row. The first row is having two non-zero values. One is 3 and the other is 4, right? So they are linked. Second row is having two non-zero values, which is 5 and 7. Third row is null. It is not having any non-zero values. All values are zeros. And the last row is having two non-zero values, which is 2 and 6. Right? So this is how we are going to place, or we are going to use list of lists to store a sparse map. Last but not the least one, using dictionaries also we can do. I hope you know what a dictionary is. A dictionary is nothing but a combination of key and value. A key, colon, value. Whenever you pick the key, the corresponding value will be invoked or can be replaced to implement the same, right? So the same. If the key field, for the key field of dictionary will be divided into two parts. One is row and the other column. So a combination, every combination of row and column will have a value. So the most or the best way to store a sparse matrix will be dictionaries, as it uses very less space. But while implementing, complexity raises a bit, but which is less costlier when compared to the memory, which gets wasted when we use an array, a linked list, or a list. In one sense, we can say it's as they have said, sequential access will be difficult, but memory point of view, storage point of view, this is the best way to store the sparse matrix. With that, I would like to conclude saying that the basic two implementations of a single linked list will be a polynomial and storing a sparse matrix. I hope you enjoyed this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.